Tonight, we're going to explore something that hides in plain sight throughout our universe. A single class of objects so extreme that they bend the fabric of reality itself, yet they can differ from each other by more than 10 orders of magnitude in mass. Some weigh less than a mountain. Others weigh more than entire galaxies. Some formed from dying stars. Others may have been born in the first moments after the Big Bang itself. Some blaze as the brightest persistent objects in the cosmos. Others drift silently through space, completely invisible. And here's what most people don't realize. Every single one of them, from the tiniest to the most colossal, is called a black hole. But that one name hides an astonishing hidden diversity. Before we go any further, if you enjoy these deep dives into the cosmos, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Everything you are about to hear rests on one deceptively simple idea. There exist regions in our universe where the geometry of space and time bends so severely that nothing which travels at or below the speed of light can ever leave. Not a photon, not a radio wave, not a single bit of information from anything that once crossed inward. And once you understand what that really means, the entire cosmic story you thought you knew starts to shift beneath your feet. Because black holes are not simply extremely dense objects. They are places where the ordinary rules of cause and effect have quietly been rewritten. A black hole is not an object in the way that a star or a planet is an object. It has no surface you could stand on. It has no shell of solid matter. It has no atmosphere in any conventional sense. What we actually mean when we say the words black hole is a region of space-time where gravity has become so intense that a specific boundary forms around it. Cross that boundary and there is no path back to the outside universe. The region beyond has been causally severed from everything else that exists. Whatever is inside can still influence deeper interior points, but nothing inside can ever again influence anything on the outside. That boundary is called the event horizon, and its name is precise. It marks the horizon beyond which no event that happens inside can ever be seen, measured, or communicated with from outside. Any information, any signal, any influence originating inside the event horizon can only continue moving further inward, never outward. The one-way character of the horizon is not a matter of engineering or technology or brute force. It is a consequence of how space-time itself curves in the presence of extreme mass and energy. There is no future path from the interior that leads back to the outside. That set of paths does not exist. Now here is the first crucial correction to a very common mental picture. The event horizon is not a solid surface. It is not a wall. It is not a membrane. If you fell toward one of the largest black holes in the universe, and if you happen to be inside a small enough capsule that tidal forces did not tear you apart along the way, you might cross the horizon without noticing anything unusual at that exact instant. There would be no jolt, no visual boundary. The horizon is a mathematical boundary of causality. The last surface from which a light signal could still, in principle, escape outward. Everything on your side of it can still send signals to the wider universe. Everything past it cannot. That distinction matters because our imaginations tend to want the event horizon to be a place. It is not really a place, it is a condition. The next important idea is that the event horizon's size grows with mass. For a non-rotating black hole, the horizon's radius is directly proportional to its mass. Double the mass, and the horizon radius doubles, Multiply the mass by 10,000 and the horizon radius grows by a factor of 10,000 as well. This is deeply counterintuitive. In everyday life, adding matter to a compact object usually makes it denser, and only a little larger. For a black hole, the horizon simply expands in step with the mass, like an inflating boundary. That scaling has a strange and important consequence. The bigger a black hole becomes, the gentler the local conditions at its horizon actually are. Tidal forces, the difference in gravitational pull between your head and your feet as you approach, depend not on total mass alone, but on how tightly the surrounding space-time is curved right where you are. For a small stellar mass black hole a few kilometers across, the curvature right at the horizon is savage. Anything falling in would be stretched into a long, thin thread of atoms. The phenomenon whimsically nicknamed spaghettification, long before crossing. For a supermassive black hole with a horizon larger than the orbit of Neptune, the curvature at that outer boundary can be so gradual that a human body could, in principle, pass through it in one piece. The extreme conditions still exist. They are just deeper inside. The horizon of a truly enormous black hole is a quieter place than a small one. So the horizon is not a wall. Its size scales with mass, and its local violence decreases as its size grows. These are not exotic footnotes. They are the foundation of everything else you're about to learn. Once you accept that a black hole is a region of space-time rather than an object with a shell, you can begin to make sense of the different features astronomers refer to when they discuss one. Because although the black hole itself is defined by the horizon, several other regions surround it, and each has been the subject of decades of careful study. The words matter, and confusing them for each other has caused a great deal of unnecessary muddle. The first is the photon region, or in the simplest, non-rotating case, the photon sphere. This is a zone just outside the event horizon where the gravitational field is so intense that light itself can orbit. A photon traveling in exactly the right direction at exactly the right distance can circle the black hole one time or many times before either falling in or escaping outward. These photon orbits are unstable, which means the slightest perturbation sends the photon inward or outward. But their existence means that some of the light we see from the vicinity of a black hole has actually looped around it, sometimes multiple times, on its way to our telescopes. Sit outside that photon region, and you begin to see what astronomers call the black hole shadow. When the Event Horizon Telescope collaboration produced the first direct image of the environment around a supermassive black hole in the galaxy M87 in the year 2019, and later the first image near the black hole at the center of our own Milky Way galaxy, called Sagittarius I star. The dark central region in those images was not, strictly speaking, a photograph of the event horizon. It was the shadow, the region where light either falls in or is deflected around the black hole, leaving an apparent darkness at the center of the surrounding glow. The shadow is generally larger than the event horizon itself, because of the way curved space-time bends light paths on their way to us. Anyone who says those images captured the event horizon directly is skipping over an important subtlety. What we saw was the shape that light cannot escape from, distorted by the enormous gravitational lensing of the black hole on itself. Then there is the accretion disk. When gas, dust, or the shredded remains of a nearby star fall toward a black hole, they very rarely fall straight in. Almost every parcel of infalling material carries some sideways motion, some angular momentum, and that sideways motion prevents a direct plunge. Instead, the material settles into a rotating disk, spiraling inward as friction and magnetic stresses slowly rob it of orbital energy. This accretion disk can become one of the brightest structures in the universe, radiating across radio, infrared, visible, ultraviolet, and X-ray wavelengths. But the disk is not part of the black hole itself. It's the material outside the black hole that happens to be in the process of falling in. When you see a stunning artist's illustration of a glowing whirl around a dark center, the glowing whirl is the disk, not the black hole. The black hole is the small dark cavity in the middle that the disk cannot fill. The innermost edge of that disk is bounded by another key feature called the innermost stable circular orbit. Inside this radius, no stable circular orbit exists for ordinary matter. A particle passing this boundary must either plunge inward or be flung out. It cannot simply circle indefinitely. For a non-rotating black hole, the innermost stable circular orbit sits at 3 times the horizon radius. For a rapidly rotating black hole, the innermost stable circular orbit can move much closer, sometimes almost touching the horizon itself, if the material orbits in the same direction as the black hole's spin. Because that inner edge determines how much gravitational energy accreting material can release as radiation before it falls in, the spin of the black hole strongly influences how brightly its disk can shine. And finally, deep inside, classical general relativity predicts a singularity. This is the point, or in the rotating case, the ring, at which the mathematics of Einstein's theory ceases to give sensible answers. Predicted densities become infinite, curvature becomes infinite, distances and times as ordinary concepts break down. It is important to be extremely careful here. The singularity is not a directly observed physical point whose true quantum nature has been mapped and understood. It is a place where the classical description of gravity gives it up. Almost every physicist studying black holes strongly suspects that whatever actually happens deep inside a real black hole is governed by a quantum theory of gravity that we do not yet possess. The classical singularity is best understood as a signal that our model has reached its limits, not as a confirmed physical object. Together, these features, the event horizon, the photon region, the shadow, the accretion disk, the innermost stable circular orbit, and the classical singularity, form the anatomy of the black hole picture. They live at different distances. They answer different questions. And they are not interchangeable. Whenever a documentary shows a black hole as a spinning, glowing sphere, most of the glow is the disk. Most of the visible dark shape is the shadow, and the actual black hole is smaller and quieter than either. Now, the obvious question. If a black hole emits no light of its own and swallows anything that crosses its horizon, how on earth do astronomers know they exist at all? The answer is one of the great success stories of modern astronomy. There are at least 7 independent detection methods, each measuring a different consequence of a black hole's presence, and their results have converged on a consistent picture that leaves essentially no reasonable doubt. The first and oldest method is watching the orbits of stars. Even the darkest object betrays itself if something visible is looping around it. In the constellation Cygnus, astronomers noticed decades ago that a bright blue supergiant star appeared to be locked in orbit around an invisible companion. Careful measurement showed the invisible companion had a mass many times that of the Sun, far too much to be a neutron star or a white dwarf, and yet emitted no light. That object, known as Cygnus X-1, became one of the first strong candidates for a stellar mass black hole in the 1970s. In the very center of our own galaxy, astronomers have spent decades tracking individual stars looping around an invisible point of extraordinary mass. One such star, known simply as S2, completes a full orbit every 16 years, sometimes swinging within a few times the size of our solar system of the invisible mass at its focus. Those orbits reveal a compact object of about 4 million times the mass of the Sun, concentrated in a region far too small to be anything but a supermassive black hole. That object is Sagittarius A star, and the observations that pin down its mass and location earned a Nobel Prize in the year 2020. The second method is X-ray emission from accreting material. As gas spirals inward toward a black hole, friction and magnetic turbulence heat it to enormous temperatures, often into the millions of degrees. That superheated gas radiates strongly in X-rays. Space-based X-ray observatories like Chandra, XMM Newton, and NuSTAR have mapped countless bright X-ray sources across the sky, and many turn out to be accreting black holes drawing material from a companion star or from surrounding gas. These systems are called X-ray binaries when the fuel comes from a companion star, and active galactic nuclei when the fuel comes from the gas reservoir at the center of a galaxy. The characteristic spectra of that X-ray light carry fingerprints of extreme gravity, signatures no ordinary star could produce. The third method is gravitational waves. When two black holes spiral inward and merge, the process itself generates ripples in the fabric of space-time. Those ripples propagate outward at the speed of light, stretching and squeezing anything they pass through by a fantastically small amount. In September of the year 2015, the LIGO detectors in the United States picked up their first confirmed signal. A chirp of gravitational waves from two black holes, each around 30 times the mass of the Sun, merging over 1 billion light-years away. Since then, LIGO, its European partner Virgo, and the Japanese detector Kagura have detected many dozens of such mergers. Gravitational wave astronomy has become a routine and powerful way to confirm the existence of stellar mass and intermediate mass black holes, and to measure their masses and spins with impressive precision. The fourth method is gravitational lensing. Any concentration of mass bends the light passing near it, a prediction of Einstein's general theory of relativity confirmed for over a century. A black hole, being a very compact concentration of mass, distorts the images of stars or distant galaxies behind it. In microlensing surveys, long-running programs that watch millions of stars for brief brightening events as a foreground mass passes in front, some of the events reveal invisible compact objects passing through the field. A small subset of those candidates are believed to be isolated, non-accreting stellar mass black holes, coasting through the galaxy without a disk or a companion to give them away. The fifth method is the tidal disruption event. Occasionally a star wanders too close to a supermassive black hole in the center of a galaxy. The tidal forces stretch the star apart, spreading its material into a stream that partly falls inward and partly is flung outward. As the infalling material accretes, it produces a dramatic flare of light that can rise over weeks and fade over months or years. Observatories now catch several of these events every year, and each one reveals a supermassive black hole in a galaxy that was otherwise dormant and would have been undetectable using its steady emission alone. The sixth method is radio imaging of black hole shadows, the method I mentioned earlier. By combining radio telescopes across the world into one Earth-sized virtual instrument through a technique called very long baseline interferometry, astronomers have produced direct images of the glowing plasma orbiting supermassive black holes and the dark central shadow they cast. The Event Horizon Telescope image of the black hole in M87 and the later image of Sagittarius A star are among the most stunning astronomical images ever made. And each provides a completely independent line of evidence for the existence and properties of the objects they show. The seventh method is astrometric wobbling. If a black hole is in a wide binary system with a visible star, and the black hole is quiet enough not to produce X-rays, the star's position will still wobble tiny amounts on the sky as it orbits the invisible companion. The European Space Agency's Gaia mission, mapping the positions and motions of over 1 billion stars, has begun to identify silent stellar mass black holes this way. These are among the first confirmed cases of black holes that emit essentially no radiation of their own and are not currently feeding on anything. They are, in a sense, dark objects with no glowing companion around them. The closest we have ever come to catching a truly quiet black hole in the act of doing nothing. Every one of these methods measures a real gravitational effect. Everyone is consistent with the same underlying picture. Everyone has revealed new populations of black holes we had no direct access to a generation ago. Between them, the evidence for the existence of black holes has moved from a mathematical curiosity in Einstein's equations, through decades of indirect inference, to direct high-resolution imaging. Before we go further, we need to clear away a persistent misconception that shapes the way most people imagine black holes. The idea that black holes are cosmic vacuum cleaners, pulling in everything around them, threatening to sweep across the universe, greedily consuming whole solar systems that stray too close. This picture is almost entirely wrong, and understanding why is essential to understanding what black holes really are. A black hole's gravitational pull, at any given distance outside its horizon, is exactly the same as the pull of any other object with the same mass at that same distance. If the sun were somehow instantaneously replaced by a black hole of exactly one solar mass, the Earth would not be sucked in. The Earth would continue orbiting along its normal orbit as if nothing had happened gravitationally. The planet would freeze, of course, because it would lose all sunlight and warmth, but its trajectory would remain nearly unchanged. Black holes do not exert any special extra pull that ordinary matter of the same mass does not. What makes a black hole extreme is not the strength of its gravity at a distance. What makes it extreme is that its mass is compressed into such a small volume that you can approach unusually close to it before you hit the horizon. And close to a compact mass, gravity naturally becomes very strong. But that same intensity would exist near any equally compact object of the same mass. The black hole is not vacuuming. You are simply able to fall much closer to the center than you could with a normal star of the same mass, because the normal star has a solid surface in the way, and the black hole does not. Material can orbit a black hole safely for as long as it retains angular momentum and stays sufficiently far outside the horizon. Stable orbits exist. Real astronomical systems contain gas clouds, star clusters, and even entire stellar populations orbiting black holes at safe distances for millions or billions of years. The black hole at the center of our galaxy has hundreds of stars looping around it in stable orbits. Some of those stars are now on their 30th or 40th loop since the invention of the modern telescope, and they show no sign of being consumed. They are simply gravitationally bound to a very massive, very compact object. The universe is not being sucked into black holes. Most black holes are surprisingly quiet, sitting placidly at the centers of galaxies or drifting through interstellar space, waiting for the rare occasions when new material happens to fall close enough to accrete. On the timescales of galaxies, that happens repeatedly. On the timescales of human civilization, most black holes barely change at all. The dramatic picture of the ravenous cosmic drain belongs to fiction. The scientific reality is closer to a still, dark region that only reveals its existence when something wanders close enough to give the game away. Now we come to the central puzzle that will guide everything that follows. Astronomers have identified 14 major ways of classifying black holes, and at first glance that number seems bewildering. Are there really 14 different kinds of black hole in the universe? 14 different physical species? The answer is that these 14 categories are not species. They are not competing labels of the same rank as the categories in a biological taxonomy. They are coordinates, describing the same underlying object from different angles. A single black hole can simultaneously be all of the following. It can be supermassive by its mass. It can be a Kerr solution by its space-time geometry, because it happens to be rotating and nearly electrically neutral. It can be actively accreting because it is currently drawing gas from its surroundings. It can be part of a binary because a second black hole is bound to it. And it can be a recoiling remnant because an earlier merger gave it a gravitational wave kick that displaced it from the galactic center. All of these labels apply at once. Each answers a different question about the same object. The mass categories, the origin categories, the space-time geometry categories, the behavior categories, and the environment categories all describe the same universe of objects. They just slice that universe along different axes. When someone asks what type of black hole an object is, the honest answer depends entirely on which question they are actually asking. How massive is it? How did it form? Does it rotate? Does it carry meaningful charge? Is it currently feeding? Is it isolated or in a binary? Is it central or wandering? Is it a directly observed population or a predicted one? Over the coming journey, we will move through these axes one at a time. We will start with the mass ladder from the smallest confirmed stellar remnants to the largest known monsters. We will follow with formation history, distinguishing objects born from dying stars from objects that may have formed in the first fraction of a second after the Big Bang. We will pass through the mathematical menagerie of space-time solutions and then examine what black holes are actually doing right now, whether they are feeding, sleeping, merging, or drifting. Along the way, we will meet the hybrid categories and edge cases, and we will finish by clearing out the imposters that sometimes get mistaken for black holes, but are not black holes at all. By the end, the 14 categories will feel less like 14 zoo enclosures and more like 14 viewing windows into the same immense object. That shift in understanding is the entire point of the journey ahead. Let's begin with the smallest members of the black hole family, the ones we understand best, and then climb the mass ladder from there. Because when astronomers sort black holes by mass, they're not simply arranging them by size for tidiness. Mass is the single most important number that determines almost everything else about a black hole. from how it formed, to how big its horizon is, to what its neighborhood looks like, to whether astronomers had any hope of finding it in the first place. The lightest confirmed black holes are the stellar mass black holes, and their name gives away their origin story. They are the corpses of massive stars. For most of a star's life, it maintains a delicate balance. The crushing weight of its own outer layers is held up by the outward pressure of energy generated by nuclear fusion in its core. Hydrogen fuses into helium, helium into carbon and oxygen, and in the most massive stars, this chain continues through neon, magnesium, silicon, and finally into iron. Iron is the end of the road. Fusing iron does not release energy, it costs energy. So when a massive stellar core builds up a large iron center, the fires that held the star up quietly go out, and the core collapses under its own weight almost instantly. What happens next depends critically on how much mass is available. If the collapsing core is below a certain threshold, the collapse is halted when its protons and electrons are crushed together to form neutrons, and a neutron star is left behind. If the core is heavier, the neutrons themselves cannot resist further collapse, and the material falls inward past the point of no return. The result is a stellar mass black hole. In some cases, the collapse is prompt, forming a black hole in a fraction of a second, and swallowing much of the outer star before it can be ejected. In other cases, a proto-neutron star briefly forms, holds itself up for a moment, and then collapses further as more material rains down onto it in what is called a fallback event. In yet other cases, a neutron star is formed first, only to later become a black hole after slowly accreting matter from a companion star or from surrounding gas. The final mass of the black hole is almost never equal to the mass of the star that produced it. Along the way, a great deal of matter is lost. Stellar winds, the constant streams of gas blown off the surface of hot, massive stars over millions of years, carry away substantial mass long before the star dies. If the star was in a binary system, its companion may have stripped its outer layers through gravitational interaction. The final explosion, if there is one, blasts most of the remaining outer envelope into space in a spectacular supernova. Only the innermost material collapses into the black hole itself. The result is that a star that began with, say, 30 times the mass of the Sun might leave behind a black hole of only 10 or 15 solar masses. One of the most important factors turns out to be metallicity, the astronomical shorthand for how much of a star's mass is made up of elements heavier than hydrogen and helium. Massive stars with high metallicity have strong stellar winds because heavy elements in their outer layers absorb radiation efficiently and are pushed outward by it. Massive stars with low metallicity, the kinds of stars that dominated the young universe, or that still exist in some pristine gas clouds today, have weaker winds and retain far more of their original mass. These low metallicity stars can leave behind heavier black holes. This helps explain why the black hole mergers detected by gravitational wave observatories often involve objects heavier than anything we ever detected as X-ray binaries. The X-ray binaries in our galaxy tend to be metal-rich systems, producing modest black holes. The gravitational wave mergers include populations from earlier or more distant environments where much heavier remnants could form. There is another wrinkle called pair instability. In extremely massive stellar cores, temperatures become so high that pairs of electrons and positrons are spontaneously produced from gamma-ray photons. Those pairs sap energy from the radiation field, weakening the pressure that holds the core up, and the whole star can become unstable. In a certain mass range, the entire star is blown apart with no black hole left at all. In an even higher mass range, the star collapses directly without exploding. This process carves an expected gap in the mass distribution of stellar origin black holes, a region where you would not naively expect many objects to be produced by pair instability physics. You may have heard talk of mass gaps in the black hole population, and this is where the phrase begins. A mass gap is not a fundamentally different kind of event horizon. There is no exotic new object hiding in the gap. A mass gap is simply a region in the observed or expected mass distribution where fewer objects than average are found, because the physics of stellar death does not favor producing them there. There is a proposed lower mass gap between the heaviest neutron stars and the lightest black holes, somewhere in the neighborhood of 2 to 5 solar masses. There is a proposed upper mass gap higher up, where pair instability effects are believed to prevent stellar cores from producing black holes in a certain range, but the observed picture has become more complicated. Gravitational wave observations have detected black holes whose masses land squarely in these expected gaps. Some detected merger components have masses in the low mass gap. Others sit in the upper mass gap. One famous event, called GW190521, involved a black hole with a mass estimated at around 85 times the mass of the Sun, which is right in the middle of the region where pair instability physics was supposed to forbid such objects from forming by direct collapse of a single star. That does not mean the physics is wrong. It means those particular black holes may not be first-generation stellar remnants at all. They may be the results of earlier mergers, or they may have formed in unusual environments. The mass gaps are real trends, not iron laws. Astronomers observe stellar mass black holes through several channels, and each has its bias. The classical channel is the X-ray binary. If a stellar mass black hole has a nearby companion star and is able to pull material off it, the accreting gas forms a small hot disk that radiates powerfully in X-rays. Cygnus X-1, the famous system in the constellation Cygnus, is one such object. The story of how Cygnus X-1 moved from suspicion to acceptance is worth telling, because it captures how the entire concept of a stellar mass black hole earned its place in mainstream astrophysics. When the system was first identified as a strong X-ray source in the 1960s, no one knew what it was. In the early 1970s, careful measurements pinned down the mass of the invisible companion at somewhere between 10 and 20 times the mass of the Sun, far heavier than any neutron star could possibly be. The most economical explanation was a black hole, but at that time no black hole had ever been directly confirmed anywhere in the universe, and the theoretical community was divided on whether nature actually formed such objects at all. In 1974, Stephen Hawking and Kip Thorne famously placed a friendly bet on the question, with Hawking wagering against Cygnus X-1 being a black hole as a form of insurance against his own theoretical work being wrong. Hawking eventually conceded the bet in 1990, once the accumulated evidence had become overwhelming. The system remains one of the most studied stellar mass black hole candidates in the sky, and every new generation of X-ray telescope has refined its mass and spin with better precision than the last. V616, Monocerotis, and dozens of others in our galaxy work similarly, but these systems are the exception. a stellar mass black hole with no companion star, drifting alone through interstellar space, is nearly invisible. It emits no light of its own. It occasionally captures a stray hydrogen atom from the surrounding gas, but the resulting radiation is far too faint to detect from any distance. The gravitational wave channel has revolutionized what we know about stellar mass black hole populations. Every merger detected by LIGO, Virgo, and Cagra is essentially a shout announcing the existence and masses of two stellar mass black holes at a specific moment when they collided. Those detections have revealed a much broader distribution of masses than the X-ray binaries hinted at. Microlensing surveys, which watch for the tiny brightening of a background star as a compact mass drifts in front of it, have caught candidate isolated stellar mass black holes. And astrometric surveys, using the Gaia mission's exquisitely precise stellar position measurements, are beginning to find silent black holes as invisible companions to visible stars, whose slight wobble reveals a dark, massive partner they cannot possibly be orbiting alone. The number of stellar mass black holes in our galaxy is estimated to be somewhere in the range of 100 million to 1 billion. Only a tiny handful have ever been individually identified. The vast majority are quiet, isolated, and unnoticed. They form a hidden population, spread throughout the disk and halo of the Milky Way, waiting for the day when their existence will be revealed by an orbital wobble, a microlensing event, or a merger with another compact object. A stellar mass black hole can grow, but not easily. Ordinary accretion is slow, even when a black hole is greedily feeding on a companion star's outer layers. Radiation pressure from the hot inflowing gas pushes back against further accretion, capping the effective rate at what astronomers call the Eddington limit. At this limit, a black hole doubles its mass on a timescale of tens of millions of years. A 10 solar mass black hole feeding steadily at the Eddington limit would take 1 billion years to reach 1,000 solar masses, and much longer to become truly massive. Mergers can help. 2 10 solar mass black holes can combine into a 19 or 20 solar mass remnant nearly instantly on cosmic timescales. But it is very difficult in the normal course of galactic life for a stellar mass black hole to accrete or merge its way into the supermassive regime. That fact plays an enormous role when we consider how the largest black holes actually came to exist. Move up the ladder and we enter one of the most controversial and observationally frustrating territories in astronomy: the realm of intermediate mass black holes. These objects bridge the enormous gap between the stellar mass population, which caps out around a few tens of solar masses, and the supermassive population, which starts at roughly 100,000 solar masses and rises from there. The intermediate range, from around 100 solar masses up to about 100,000 solar masses, has been the subject of decades of searching. Only in recent years has confirmed evidence begun to accumulate. The reason intermediate mass black holes matter so much is that they are the missing link. Supermassive black holes exist today with masses of millions or billions of solar masses. Something had to happen between the first stellar mass seeds and those enormous adult objects. Intermediate mass black holes should have been a natural way station on the growth path, yet finding them has proved extraordinarily hard. Part of the problem is that intermediate mass black holes are typically found in environments where confusion reigns. A cluster of stellar remnants can, in some observations, mimic the gravitational signature of a single black hole of intermediate mass. A rapidly accreting stellar mass black hole can, under certain conditions, appear as bright as a much larger, slowly accreting one. And a supermassive black hole inside a very small dwarf galaxy can look like an intermediate mass black hole from a distance. Sorting real intermediate mass detections from these lookalikes has been painstaking. Several formation possibilities have been proposed. In dense star clusters, especially the ancient globular clusters that swarm around galactic centers or float in galactic halos, black holes can form and then sink to the center through dynamical friction. Once concentrated, they can merge repeatedly, building up an intermediate mass object over hundreds of millions of years. In the youngest and densest star clusters, massive stars themselves can collide and merge before they die, producing a runaway growth of a single ultramassive star whose eventual collapse leaves behind an intermediate mass black hole in one step. In some models of the young universe, the very first stars to form, often called population 3 stars, reached masses of hundreds of solar masses. Their collapse would have produced direct intermediate mass seeds in the first hundreds of millions of years after the Big Bang. And in some scenarios, giant clouds of gas at the centers of primordial galaxies collapse directly into massive objects without ever forming ordinary stars along the way. Different intermediate mass black holes may have different origins. There is probably no single formation channel. The population, if it exists in the numbers models predict, is a mosaic. Candidate evidence has come from several directions. Some globular clusters show central concentrations of stars whose motions suggest an unseen massive object at the middle, though the interpretations remain contested. Some nuclear star clusters at the centers of small galaxies show similar signatures. Certain ultraluminous X-ray sources, points of anomalously bright X-ray emission scattered across nearby galaxies, have been argued to be intermediate mass black holes accreting at high rates. But it now appears that most ultraluminous X-ray sources are stellar mass black holes or neutron stars accreting at super Eddington rates through funnel geometries, not intermediate mass objects. A few outliers remain plausible intermediate mass candidates, but not all of them. Tidal disruption events have added new evidence. When a star is ripped apart by a black hole, the resulting flare has a characteristic timescale, temperature, and luminosity that depend on the black hole's mass. A handful of tidal disruption events have been observed in low-mass galaxies where the central black hole appears to be in the intermediate mass range. Some of the cleanest evidence has come from gravitational waves. The GW190521 event, mentioned earlier, produced a remnant of about 140 solar masses, squarely inside the intermediate range. Every subsequent detection of a massive merger remnant extends the confirmed intermediate mass population. We should be careful not to overclaim. Intermediate mass black holes have not yet been identified as completely and routinely as stellar mass or supermassive black holes. The candidates are growing in number and quality, but many individual claims remain under debate. Still, the category has moved decisively out of the realm of pure hypothesis and into the realm of confirmed but sparsely mapped populations. In another decade or two, it may look as ordinary as the stellar mass or supermassive regimes do today. Continue up the mass ladder, and we arrive at the black holes that dominate the centers of most large galaxies. the supermassive black holes. Their masses range from around 100,000 solar masses to more than 10 billion. There is no perfectly universal boundary at the low end. Astronomers have detected central black holes in dwarf galaxies with masses in the hundreds of thousands, which some classify as supermassive and others as intermediate mass. But when we move firmly into the millions and billions, we are unambiguously in the supermassive realm. Almost every large galaxy studied in detail contains a central, supermassive black hole. Our own Milky Way hosts Sagittarius E star, weighing about 4 million times the mass of the Sun. The nearby Andromeda galaxy hosts a black hole roughly 100 million times the mass of the Sun. The giant elliptical galaxy M87 in the Virgo cluster hosts a black hole of about 6.5 billion solar masses. The very object whose shadow was captured in the first Event Horizon telescope image. Further out, the quasar TON 618 may host a black hole approaching the 60 billion solar mass mark, though estimates for the largest objects carry significant uncertainties. Measuring the masses of these central giants is a technical art form. For the closest cases, astronomers can watch individual stars orbit the center directly, as with the S-star cluster around Sagittarius IY star. For more distant galaxies, they measure the motion of gas clouds around the nucleus, using the way spectral lines from those clouds shift with velocity. In some galaxies, they detect matter emission from molecules in an orbiting disk, which acts like a natural set of speedometer readings at known radii. In active galaxies, they use a technique called reverberation mapping, in which they time the delay between fluctuations in the central engine's brightness and the corresponding echo in surrounding gas clouds. Each technique has its assumptions, but where they overlap, they agree, and modern surveys have measured central black hole masses for hundreds of galaxies. The event horizons of supermassive black holes can be enormous by human standards. The horizon of the Milky Way's central black hole is around 24 million kilometers across, roughly 1/3 of the average distance from Mercury to the Sun. The horizon of M87's black hole is roughly the size of our entire solar system, dozens of astronomical units across. The horizon of TON 618 would swallow the orbit of Neptune many times over. Yet these enormous objects, gargantuan by comparison to a stellar mass black hole, still make up a tiny fraction of their host galaxy's mass. A supermassive black hole typically contains less than 1 part in 1,000 of its galaxy's total mass. The rest is in stars, gas, dust, and dark matter spread over tens of thousands of light years. Despite that mass ratio, the central black hole and its host galaxy are strongly linked. Observations have revealed a tight correlation between the mass of the central black hole and the mass, luminosity, and velocity dispersion of the host galaxy's central bulge. Bigger bulges hold bigger black holes. This correlation is one of the great empirical discoveries of modern astrophysics. It suggests that the growth of black holes and the growth of galaxies are not independent processes. They are coupled. This specific version of this correlation that has been studied most intensively is called the M-sigma relation, connecting the mass of the central black hole to the velocity dispersion of stars in the surrounding bulge, essentially how fast those stars are moving on average as they orbit through the galactic center. The relation is remarkably tight. Across galaxies spanning many orders of magnitude in bulge mass, the central black hole's mass tracks the stellar velocity dispersion with striking regularity. When this correlation was first firmly established at the turn of the millennium, it came as a genuine surprise. The central black hole contains only a small fraction of the galaxy's total mass, and its gravitational influence extends over a region tiny compared to the galaxy as a whole. How could such a small object know about and coordinate with the properties of a structure 1 billion times its own size? The leading explanation involves feedback. When a supermassive black hole is actively accreting, the enormous radiation and outflowing winds from its immediate environment can heat and blow away large amounts of gas throughout the host galaxy's inner region. That expelled gas is no longer available to form new stars, and it is no longer available to feed the black hole itself. The result is a self-regulating loop. A black hole that grows too fast for its host will blow away its own fuel supply. A galaxy whose black hole is undermassive relative to its bulge will keep delivering gas until the black hole catches up. Over billions of years, this feedback settles both quantities into a joint equilibrium described by the observed correlation. Whether this specific picture is exactly right, or whether other mechanisms such as merger regulation dominate the coupling remains debated. But the fact that central black holes and galactic bulges evolve together, not independently, has become one of the most important insights in extragalactic astronomy. Correlation, of course, is not proof of a simple one-way causal chain, and the direction and dominant mechanism of the coupling remain active areas of research. How do supermassive black holes grow to their observed sizes? 3 main routes are on the table. First, prolonged gas accretion. A supermassive black hole can steadily draw material from a large reservoir of gas in the galactic center, growing at rates close to the Eddington limit for extended periods. Second, mergers between smaller black holes. As galaxies collide and combine, their central black holes eventually sink toward each other and merge, adding their masses. Third, consumption of individual stars. Every time a star wanders too close, a fraction of its mass ends up inside the horizon. But even combining all 3 routes, there is a serious puzzle. Astronomers have detected quasars powered by supermassive black holes of 1 billion solar masses at cosmological redshifts corresponding to less than 1 billion years after the Big Bang. In some cases, they have detected such objects at only 700 million years after the Big Bang. Growing a stellar mass seed of a few tens of solar masses into 1 billion solar mass supermassive black hole in less than 1 billion years, even at continuous Eddington limited accretion, is very tight. Something must have jump-started their growth. This is called the seed problem. Several possible seeds have been proposed. Remnants of the first massive stars could have provided black hole seeds of a few hundred solar masses, but they would need to accrete continuously for the full time available with almost no interruption to reach 1 billion. Direct collapse black holes, in which a massive gas cloud in the early universe collapsed straight into a black hole of 10,000 to 100,000 solar masses without ever forming a normal star, would offer a much better head start. Runaway stellar collisions in dense primordial clusters could have built up massive black hole seeds in a similar range. And in the more speculative direction, primordial black holes formed in the very first fraction of a second after the Big Bang could, in principle, seed later supermassive black holes as well, though this is not the mainstream explanation. The existence of very massive quasars in the very early universe constrains all of these ideas, but has not yet chosen between them. A supermassive black hole does not have to be active. Most of them, at any given moment, are not. The bright quasars and active galactic nuclei that light up cosmological surveys represent the small minority of supermassive black holes that happen to be feeding voraciously at that moment. The majority are dormant, sitting quietly at the centers of their galaxies with little gas flowing inward, radiating essentially nothing. Sagittarius A star, in our own galaxy, is one of these quiet objects at present. It occasionally flares when a small clump of gas falls in, but overall it is far below the Eddington limit, and produces very little light. It would be undetectable by any of the classical quasar surveys if we were observing our galaxy from a great distance. The supermassive black hole in the Milky Way is not a quasar. It is a dormant giant, and most of the universe's supermassive black holes are the same. At the extreme upper end of the supermassive population, we find objects that some astronomers casually label as ultramassive. This is not a new species. It is not a fundamentally different solution to Einstein's equations. It is simply a nickname for the very largest black holes we have measured. There is no universally agreed threshold, but the ultramassive label is commonly attached to black holes above 10 billion solar masses, and increasingly to any black hole above roughly 5 billion. Ultramassive black holes are almost always found in the same class of environment, the very brightest and most massive galaxies at the centers of galaxy clusters, so-called brightest cluster galaxies. These are enormous elliptical galaxies formed through the merger of many smaller galaxies over billions of years. Each merger delivered another supermassive black hole to the central galaxy, and those black holes eventually sank inward and combined. The result is a single central object whose mass is the accumulated inheritance of dozens or hundreds of earlier galactic mergers. The black hole at the center of the cluster galaxy, Holmberg 15A, in a cluster roughly 700 million light-years away, has been estimated at around 40 billion solar masses. The quasar TON 618 already mentioned may host something close to 60 billion. The elliptical galaxy NGC 1600 hosts one estimated at around 17 billion solar masses. Estimates for individual objects continue to shift as new methods refine or reduce older numbers. Measuring these masses is genuinely difficult. The techniques that work beautifully for a nearby galaxy like Andromeda become severely limited at cosmological distances. Astronomers must rely on assumptions about the shape of the galaxy's gravitational field, the distribution of stars and dark matter, the geometry of gas flows, and the distance to the object. Small errors in any of these can produce large errors in the inferred black hole mass. The most extreme claimed values should be treated with appropriate caution. A claim of 100 billion solar mass central black hole in some far-off system is a possibility, not a firmly established fact, and different research groups can arrive at very different estimates for the same object using different methods. There are also physical reasons to expect a rough ceiling on how massive a black hole can become in the observable universe. Feedback from an actively accreting black hole heats and blows away the surrounding gas, cutting off further accretion. The available fuel supply in the host galaxy is finite. The time since the Big Bang is finite. The merger history of a galaxy is limited by the density of its cosmic environment. Together, these constraints suggest that black holes above a few tens of billions of solar masses are already rare, and objects much larger than that face increasing difficulty growing further within the age of the universe. This is not a hard mathematical limit like the horizon mass relation. It is a practical upper bound imposed by cosmic conditions. Named record holders come and go. As observations improve, previously claimed extreme values are sometimes revised downward. New candidates are sometimes proposed and later confirmed. What is stable is the recognition that black holes of tens of billions of solar masses exist at the centers of the largest galaxies in the universe. They are simply the extreme end of a continuous, supermassive distribution. They are not a separate kind of black hole. They are the same kind of black hole, at a scale that borders on the absurd. Looking across this mass ladder, stellar, intermediate, supermassive, ultramassive, you can see one of the most extraordinary facts about the black hole population. From a compact stellar remnant of a few solar masses to a monster of tens of billions of solar masses, the range spans more than 10 orders of magnitude in mass. Nothing else in astronomy comes close. There is no other class of object where the largest examples are 10 billion times more massive than the smallest. And yet each of these objects, from the tiniest to the most colossal, is defined by the same physical condition, a region of space-time bounded by an event horizon. The mass ladder is a ladder of scale, not a ladder of different physics. It is the same object, from a whisper to a scream. Every category we have explored so far has been about mass, but mass is only one axis of the classification. Now we turn to a completely different question. Not how heavy is it, but how did it come to exist in the first place? Because black holes are believed to be born through several very different physical processes, and the same mass can be reached through more than one road. Two black holes of identical mass, sitting side by side, may have arrived there through histories that could not be more different from each other. The most familiar formation route we have already met. A massive star exhausts its fuel, its core collapses, and a stellar mass black hole is left behind. Mergers between compact objects then create heavier remnants. Prolonged accretion and repeated mergers over billions of years grow those seeds into the supermassive giants at galactic centers. This is the astrophysical channel. It relies entirely on stars, gas, and gravitational interactions playing out inside evolving galaxies. Every stellar mass, intermediate mass, supermassive, and ultramassive black hole that fits into that picture is astrophysical in origin. But there is another proposed origin story, and it does not require any stars at all. It reaches back to the earliest fraction of a second after the Big Bang, when the universe was denser than any environment that has ever existed since. In that extreme phase, tiny fluctuations in the density of matter and energy were being stretched, amplified, and stirred by the physics of the young cosmos. According to some models, in regions where the density happened to exceed a critical threshold, gravity could have overwhelmed pressure directly, causing collapse into black holes without ever needing a star to die first. These hypothetical objects are called primordial black holes. The word primordial refers to origin, not to mass. This is a crucial distinction that trips up almost every casual description. A primordial black hole could, in principle, have almost any mass. The mass depends on which era of the extremely young universe it collapsed in, and how large the collapsing region was. Some formation models predict primordial black holes as light as a small mountain, weighing only a few billion metric tons compressed into a size smaller than a single atom. Other models predict primordial black holes of one solar mass, or of hundreds of solar masses, or even of thousands. There is no single expected mass for a primordial black hole. There is a spectrum of possibilities, each tied to specific assumptions about early universe physics. Primordial black holes have never been directly confirmed, No specific candidate object has been definitively identified as one. What we have is a long history of searches designed to test whether they exist, and, if they do, in what mass ranges and abundances. The interest in these objects is intense for several reasons. If they exist in sufficient numbers, they could account for at least part of the mysterious dark matter that dominates the universe's mass budget. If they exist even in smaller numbers, they could seed the supermassive black holes at galactic centers, offering a solution to the puzzle we discussed earlier about how billion solar mass black holes appeared only a few 100 million years after the Big Bang. And if their properties can be measured, they would open a window onto physics at energy scales completely beyond the reach of any Earth-based experiment. Searches for primordial black holes proceed in several directions, each sensitive to a different mass range. Microlensing surveys watch for the temporary brightening of a background star as a compact object passes in front of it, gravitationally focusing the star's light. Long-running programs monitoring millions of stars in the Large Magellanic Cloud and elsewhere have set stringent limits on how many primordial black holes there can be in certain mass ranges without producing more microlensing events than we observe. For very small primordial black holes, in a mass range where Hawking radiation from evaporation would be intense, gamma-ray telescopes have looked for the characteristic bursts that ought to accompany the last stages of an evaporating black hole. None have been convincingly detected. For the more massive range, gravitational wave observatories have watched for mergers of black holes with masses and ranges that would be difficult to explain through stellar collapse. Some of the detected mergers, especially those involving objects in the classical mass gaps, have been discussed as possible primordial candidates, though astrophysical explanations remain viable for all of them. The result of decades of searching is a patchwork of constraints. Across many mass ranges, the fraction of dark matter that could be primordial black holes has been squeezed to very small values. In a few remaining windows, particularly in a range around asteroid masses that microlensing cannot easily probe, primordial black holes could still, in principle, make up a substantial fraction of dark matter without violating any current observation. But those remaining windows depend sensitively on the specific formation model, on the assumed mass distribution, and on the particular datasets used. It would be misleading to say that primordial black holes have been ruled out. It would be equally misleading to say they have been confirmed. What is honest is that the possibility remains open in certain narrow regions of parameter space, and the search continues. You will sometimes hear it said that a specific unusual gravitational wave event proves that primordial black holes exist. This claim goes further than the evidence justifies. A merger involving a black hole with an unusual mass is suggestive, because it hints at a formation route beyond the classical stellar channel. But being suggestive is not the same as being conclusive. Every such event has viable astrophysical explanations. Dynamical formation in dense clusters, hierarchical mergers of earlier remnants, formation from very low metallicity stars in the early universe, and other paths. Distinguishing a primordial black hole from a mundane astrophysical black hole with an unusual formation history remains an open observational problem. We do not yet have a signature that unambiguously identifies primordial origin. Related to the primordial category is another idea often confused with it: the microscopic or quantum scale black hole. Microscopic here refers to size or mass, not to origin. A microscopic black hole is simply one whose horizon is much smaller than the horizon of any stellar mass black hole. Its Schwarzschild radius could be smaller than an atomic nucleus, or smaller than a proton, or in the most exotic models, smaller than the scales at which our current theories of physics can even be defined. A microscopic black hole could arise in several ways. It could be primordial, formed in the early universe from a small collapsing region. It could arise in some highly speculative models from ultra-high energy particle collisions if certain scenarios involving extra dimensions of space happen to be correct. Or it could exist as a purely theoretical construct that quantum gravity might one day tell us how to interpret. But the important thing to keep clear is that microscopic and primordial are not the same word. A microscopic black hole may or may not be primordial. A primordial black hole may or may not be microscopic. The reason microscopic black holes are so interesting is that they connect directly to one of the most beautiful results in theoretical physics: Hawking radiation. In the early 1970s, Stephen Hawking showed that when the principles of quantum field theory are applied carefully to the region just outside a black hole horizon, the black hole cannot simply be dark, it must radiate. Not because particles somehow escape from inside the horizon, which the geometry of space-time absolutely forbids. Rather, because the presence of the horizon changes the quantum properties of the surrounding vacuum in a way that produces a stream of outgoing particles at a very specific temperature. The temperature is astonishingly small for astrophysical black holes. For a stellar mass black hole, the predicted Hawking temperature is only a few nanokelvin, far colder than the cosmic microwave background that fills the universe. Such a black hole gains far more energy from absorbing the ambient cosmic microwave radiation than it loses from Hawking radiation. It grows, on balance, rather than shrinking. For a supermassive black hole, the temperature is even lower, essentially undetectable against any conceivable background. Under the conditions of the modern universe, astrophysical black holes are effectively not evaporating at all. Their Hawking radiation is a real theoretical prediction, but its intensity is far below anything we could ever detect from a distance. The situation changes dramatically for microscopic black holes. Hawking temperature is inversely proportional to mass. As mass goes down, temperature goes up. A black hole with the mass of a small mountain would radiate at a temperature of billions of degrees, emitting a stream of high-energy particles and gamma rays. As it radiates, it loses mass, which raises its temperature, which increases the rate of radiation. This runaway process ends in a final flash, a rapid burst of extremely energetic radiation as the last measurable fraction of the black hole's mass is emitted in a fraction of a second. If primordial black holes formed with certain masses in the early universe, they would be reaching the endpoint of this evaporation process right around now. Gamma ray observatories have looked for the expected bursts. None have been convincingly detected. This absence sets meaningful upper limits on how many primordial black holes of that particular mass range can exist per unit volume. And whatever the very final stage of Hawking evaporation actually looks like, because a full description would require a working theory of quantum gravity that we do not yet possess. The general prediction that small black holes evaporate quickly has become one of the anchor points of modern black hole physics. Hawking radiation is only the visible tip of a much deeper theoretical structure. When Hawking's calculation was combined with earlier work by Jacob Bekenstein in the early 1970s, an astonishing picture emerged. Black holes are thermodynamic objects. They have a temperature, given by the Hawking formula. They have an entropy, given by a quantity proportional to the area of their event horizon. And they obey a set of laws that mirror the ordinary laws of thermodynamics with startling exactness. The first law of black hole mechanics relates changes in mass to changes in area, angular momentum, and charge, in a formal analogy to the first law of thermodynamics, relating changes in energy to changes in entropy and other conserved quantities. The second law states that the total horizon area of an isolated black hole can only increase over time, mirroring the second law of thermodynamics that says total entropy can only increase. The third law states that no physical process can reduce a black hole's surface gravity to zero in finite time, mirroring the third law of thermodynamics that says absolute zero cannot be reached. Before Hawking's calculation, this analogy could have been dismissed as mathematical coincidence. After his calculation, it was clear that the analogy is exact. Black holes really are thermodynamic systems, and their entropy really is a physical quantity. The specific formula for that entropy is one of the most beautiful results in all of theoretical physics. Every black hole carries an entropy equal to 1/4 of the area of its horizon, measured in units of the Planck area. An extraordinarily small unit set by the fundamental constants of nature. This means that even a modest astrophysical black hole carries an entropy that dwarfs the entropy of any ordinary object of comparable mass. A supermassive black hole at the center of a large galaxy carries entropy that dwarfs the entropy of the entire visible cosmos outside it. Whatever the microscopic origin of this entropy turns out to be, the number of internal quantum states corresponding to a single macroscopic black hole is inconceivably vast. This is the Bekenstein-Hawking entropy, and it has become one of the anchor points that any successful theory of quantum gravity must reproduce. But Hawking's calculation also produced a puzzle that has troubled physicists for half a century: the black hole information paradox. In ordinary quantum mechanics, information about the state of any system is preserved as it evolves. If you burn a book, in principle, the exact quantum state of every particle in the smoke, ash, and radiation retains all the information about the original book. That information is scrambled beyond any practical possibility of recovery, but it is not destroyed. The laws of quantum mechanics are unitary. Information is conserved. Hawking's calculation, taken at face value, suggested that black holes violate this principle. The radiation emerging from an evaporating black hole appears to be perfectly thermal, carrying no information about what fell in. If the black hole eventually evaporates completely, then the detailed quantum information about everything that was ever swallowed appears to have vanished from the universe. Entire galaxies could fall into a black hole, and their quantum information would seem to be permanently erased. That conclusion is deeply incompatible with the foundations of quantum mechanics, and it has driven decades of theoretical work aimed at figuring out where the resolution actually lies. Most researchers now believe that the information is not truly lost. Somehow, subtle correlations in the Hawking radiation preserve everything that fell in, even though the radiation looks thermal on the surface. Recent theoretical progress involving concepts called quantum extremal surfaces and entanglement islands has provided the first calculations in which the information does return, as unitary quantum mechanics demands. But the physical mechanism by which this happens in a real evaporating black hole remains under active investigation. The information paradox is not just an abstract puzzle. It is the sharpest known collision between quantum mechanics and general relativity, and its resolution is expected to teach us something fundamental about how gravity behaves at its deepest level. You will occasionally see claims that particle accelerators produce microscopic black holes. Under the scenarios that made this a live question in the 2000s, involving extra dimensions of space, a black hole produced in a collision would evaporate essentially instantaneously through Hawking radiation. No accelerator experiment has ever detected such a signature. Every attempt to search for these products has come back empty. The idea that ordinary experiments could produce dangerous, long-lived microscopic black holes has been thoroughly examined and comprehensively ruled out on multiple grounds. Nothing about the search for microscopic black holes should worry anyone about the safety of collider physics. So the origin-based classification gives us two hypothetical additions to the astrophysical population. Primordial black holes, potentially spanning an enormous mass range, hypothetically formed in the first fraction of a second of the universe, still unconfirmed, but not excluded across all mass ranges. Microscopic black holes, defined by their size rather than their history, potentially primordial, potentially produced by exotic processes, all of which would evaporate rapidly through Hawking radiation. Both remain more theory than observation. Both remain live research areas. Neither should be conflated with the well-observed astrophysical categories. Now we turn to a completely different axis of classification, one that lives entirely within the mathematics of general relativity. Because when Einstein's field equations are solved under the assumption of a stationary black hole in isolation, only three properties describe the resulting spacetime as seen from far away: mass, angular momentum, electric charge, nothing else. All the details of what fell in, the composition of the collapsed matter, its color, its temperature, its history, vanish behind the horizon and leave no external imprint. Only those three numbers survive. This is the famous no-hair result, so named because the black hole retains no distinguishing features beyond those three. That result has a beautiful consequence. Within classical general relativity, coupled to electromagnetism through the Einstein-Maxwell equations, under the relevant assumptions, there are exactly four stationary black hole solutions, corresponding to the four ways of turning those three parameters on or off. This is not a taxonomy of populations. It is a taxonomy of geometries. Every astrophysical black hole can, in principle, be described by one of these four exact solutions. Though real objects are approximations rather than mathematically pure examples. The first solution is the Schwarzschild black hole, named after Karl Schwarzschild, the German physicist who found the solution while serving on the Russian front in the First World War in 1916, only months after Einstein published his field equations. Schwarzschild described a black hole with mass and nothing else, no spin, no charge, spherically symmetric, perfectly still with respect to the surrounding space-time. This is the simplest possible black hole geometry. It is the version drawn in every introductory textbook. It is the setup used to introduce the event horizon, gravitational time dilation, the photon sphere, and the shadow. The Schwarzschild solution is an idealization, Real astrophysical black holes are unlikely to have exactly zero angular momentum. Even the smallest amount of accreting material carries angular momentum, transferring it to the black hole. Any asymmetric collapse of a spinning stellar core, or any merger with even a modestly rotating partner, endows the resulting black hole with some spin. So the Schwarzschild solution is not describing a separately formed population of non-rotating black holes waiting to be discovered. It is describing a limiting case that real black holes approach only approximately. But it remains an extraordinarily useful case, both pedagogically and for calculations involving slowly spinning objects where the corrections due to spin are small. Move to the next solution, and we allow the black hole to rotate. This is the Kerr solution, discovered by the New Zealand mathematician Roy Kerr in 1963, almost 50 years after Schwarzschild, and much harder to derive. Kerr black holes have mass and angular momentum, but no charge. They are almost certainly the correct description of the vast majority of real astrophysical black holes. Because rotation is expected to be common, and net electric charge is expected to be tiny. Around a rotating black hole, the geometry does something no other physical system can do. It drags the very fabric of space-time along with the rotation. This is called frame dragging. Near a Kerr black hole, an object cannot remain stationary with respect to distant stars. The rotation of the space-time literally forces every nearby object to co-rotate to some degree. This effect has a name that predates the discovery of the Kerr solution by decades. In 1918, Austrian physicists Josef Lenzi and Hans Thirring showed that Einstein's field equations predicted a version of this same phenomenon around any rotating mass, not only black holes. The Lenz-Thirring effect states that a rotating body drags the space-time around it into co-rotation at a rate that decreases with distance from the body. The Earth itself, rotating on its axis, drags space-time with it, though at a rate so small that measuring it required exquisitely sensitive instruments. That measurement was carried out by the Gravity Probe B satellite, launched by the National Aeronautics and Space Administration in the year 2004. The mission carried 4 gyroscopes machined to be among the most perfectly spherical objects ever constructed, and it measured how their axes drifted over time as the satellite orbited a rotating Earth. The predicted Lenz-Thirring drift was tiny, about 37 milliarcseconds per year, and yet the measurements confirmed general relativity's prediction with substantial precision. Frame dragging around a rotating black hole is the same effect turned up to its most extreme setting, so violent near the horizon that no observer can resist being carried along with the rotation. It is one of the most bizarre and one of the most experimentally confirmed predictions of Einstein's theory. Even a photon fired directly against the direction of a Kerr black hole's spin will be dragged forward with the rotation, though it can still escape outward if it starts outside a certain boundary. That boundary defines a new region unique to rotating black holes, the ergosphere. The ergosphere sits outside the event horizon and inside a surface called the static limit. Inside the ergosphere, no observer can remain motionless as seen from outside. They must co-rotate. But the ergosphere is not itself the horizon. An object entering the ergosphere can still escape back out, provided it never crosses the event horizon that lies deeper within. The name ergosphere comes from the Greek word for work, because it is theoretically possible to extract rotational energy from the black hole by exploiting motion inside this region. In one thought experiment, first proposed by Roger Penrose an object enters the ergosphere, splits into two pieces, and sends one piece outward with more energy than the entire original had before, at the cost of some of the black hole's rotational energy. The Penrose process is a real theoretical result, though extremely difficult to realize in practice. More relevant for real astrophysical systems is a related mechanism involving magnetic fields, in which magnetized plasma in the ergosphere can tap into the black hole's rotation and channel that energy into powerful outflows. This is thought to power the enormous relativistic jets seen shooting out from many active galactic nuclei. But note carefully, the jets do not originate from inside the event horizon. They are powered by extraction of rotational energy from the surrounding curved spacetime and by magnetic fields threading the region outside the horizon. Matter and light inside the horizon can never come back out. It is the exterior spin, coupled to the exterior magnetic environment, that does the work. The innermost stable circular orbit around a Kerr black hole depends on both the amount of spin and the direction of the orbit relative to that spin. For an object orbiting in the same sense as the black hole's rotation, a prograde orbit, the innermost stable circular orbit can move much closer to the horizon than it does around a non-rotating Schwarzschild black hole. For a maximally spinning Kerr black hole, the prograde innermost stable circular orbit sits nearly at the horizon itself. For a retrograde orbit, going against the rotation, the innermost stable circular orbit is much farther out. This has enormous consequences for accretion disks. A prograde disk around a rapidly spinning black hole can extract far more gravitational energy from infalling material, up to about 42% of the rest mass energy, before that material crosses the horizon. That efficiency is higher than any nuclear fusion process. It is what allows accreting supermassive black holes to become among the most luminous persistent objects in the entire universe. Measuring the spin of a real black hole is difficult, but has become routine over the last 2 decades. Several methods have been developed. X-ray reflection spectroscopy studies how X-rays from the accretion flow bounce off the inner disk and become distorted by the extreme gravity near the innermost stable circular orbit. The specific shape of certain ion emission lines in that reflected light encodes information about how close the disk can extend to the horizon, which depends on the spin. Thermal disk fitting compares the temperature and luminosity of the inner disk to models based on general relativity. Gravitational wave detections of black hole mergers reveal information about the spins of the merging black holes and the final remnant through the shape of the waveform. Future precision imaging with next-generation Event Horizon Telescope observations may allow direct measurement of the size and shape of the shadow as a function of spin. Each of these methods carries model dependence and uncertainty, but where they overlap, they broadly agree, and the picture that has emerged is one of real astrophysical black holes, with spins spanning the full range from nearly zero to close to the theoretical maximum. The behavior of spin over time is one of the most interesting stories in black hole astrophysics. A black hole growing by prolonged accretion of gas from a disk in one steady orientation will tend to spin up, because it is receiving angular momentum along a consistent axis. A black hole growing by chaotic accretion, where episodes of feeding come from many different directions over time, may end up with a much lower average spin, because the incoming angular momentum tends to cancel, and a merger between 2 black holes can produce a remnant with a spin that depends on the masses and spins of the participants. sometimes leaving a remnant spinning nearly as fast as physically allowed, sometimes leaving one with only modest spin. So real supermassive black holes carry, in their present spin, a fingerprint of their entire growth history. Now consider the third solution. What happens if we allow charge but no spin? This is the Reissner-Nordström black hole, named after the German physicist Hans Reissner and the Finnish physicist Gunnar Nordström, who worked out the solution in the 1916 through 1918 period. The Reissner-Nordström solution describes a black hole with mass and electric charge, but no rotation. Its geometry differs from Schwarzschild in subtle but important ways. In particular, it has not one horizon, but two. An outer event horizon, which is the causal boundary in the ordinary sense, and an inner horizon, which is a Cauchy horizon separating the classical predictable region from a region where classical general relativity loses its predictive power. The reason we do not expect to find real Reissner-Nordström black holes in the sky is straightforward. The universe is filled with charged particles, free electrons, free protons, ionized gas. If a black hole ever carried a significant positive charge, it would attract negative charges from the surrounding plasma at extraordinary rates, rapidly discharging until its net charge was essentially zero. If it carried a negative charge, the reverse would happen. The universe simply does not permit an astrophysical black hole to hold onto a large net charge for any appreciable length of time. So Reissner-Nordström solutions are extremely useful theoretical objects for studying horizon physics, black hole thermodynamics, and modifications of general relativity, but they are not expected to describe real black holes we observe in nature. A real astrophysical black hole may carry a tiny transient charge as ambient plasma fluctuates, but nothing approaching the extremal charged case. The extremal case is worth mentioning briefly. There is a specific charge for any given mass at which the two horizons of a Reissner-Nordström solution merge into one, and the black hole becomes maximally charged. Beyond that limit, the solution ceases to describe a black hole at all, and instead describes a naked singularity. The extremal charged black hole is a mathematical limit, not a confirmed astronomical object. Whether nature actually permits any object to reach the extremal state is one of the open questions of black hole physics, and is closely connected to the cosmic censorship conjecture, which holds that singularities should always be hidden behind horizons, rather than exposed to distant observers. The fourth and most general solution combines everything. This is the Kerr-Newman black hole, describing an object with mass, spin, and charge. It was worked out in the mid-1960s as a synthesis of the Kerr and Reissner-Nordström results. Under the standard assumptions of classical Einstein-Maxwell theory, the Kerr-Newman solution is the most general stationary black hole solution possible. Any black hole in this framework, no matter its detailed history, should settle down to a Kerr-Newman geometry described by its three external parameters. This is one of the meanings of the no-hair result. The endpoint of gravitational collapse is characterized entirely by mass, spin, and charge, with all other details vanishing behind the horizon. Because the net charge of real astrophysical black holes is expected to be negligible, the Kerr-Newman solution is more scientifically important than observationally common, but it remains theoretically indispensable. It provides the framework in which the general problem of black holes coupled to electromagnetism is analyzed. It clarifies how spin and charge together shape the horizons, the ergosphere, and the allowed motions of test particles nearby. And it provides a bridge to the deeper theoretical questions of black hole thermodynamics, entropy, and information, in which the interplay between gravitational and electromagnetic properties has yielded some of the most beautiful results in modern physics. It is worth being explicit about what these four solutions are and are not. They are not four different mass populations. A Schwarzschild geometry could in principle describe a black hole of any mass, from stellar to supermassive to ultramassive. A Kerr geometry likewise. The mass ladder and the geometry family are two independent axes of classification. An intermediate mass black hole spinning rapidly would be described by the Kerr solution. A supermassive black hole in a nearly non-rotating state would be described by the Schwarzschild solution as a first approximation. For observational purposes, the mass ladder and the geometry family together locate any real astrophysical black hole, primarily along the Kerr axis. The four solutions differ in which of the three no-hair parameters are turned on. Schwarzschild, mass only. Kerr, mass and spin. Reissner-Nordstrom, mass and charge. Kerr-Newman, mass, spin, and charge. All other properties of a stationary black hole in classical general relativity are inherited from those three numbers. Everything you would ever want to know about the outside space-time is fixed by them. This may seem like a strangely stripped-down description of something as dramatic as a black hole, but that is precisely the point. The no-hair result was one of the most surprising discoveries in 20th century physics. That the external geometry of a black hole carries so little information about the matter that fell in to make it. Two stars of completely different compositions, forming black holes of the same mass, spin, and charge, produce indistinguishable external geometries. The horizon washes away detail. It is a great cosmic eraser, keeping only three numbers and letting everything else vanish beyond retrieval. The name no-hair was coined by John Archibald Wheeler in 1971, in the loose spirit of saying that a black hole has no hair, no distinguishing features beyond the three parameters. The formal proof of this statement developed over the following years through the work of Werner Israel, Brandon Carter, David Robinson, and Stephen Hawking, among others. Their combined theorems established that in classical general relativity, coupled to electromagnetism, the only stationary, asymptotically flat, non-degenerate black hole solutions are the four we have described. Anything else you might try to build with additional structure, some hidden magnetic property, some remaining trace of the collapsed matter, some baryon or lepton signature, is forbidden by the theorems. But the no-hair statement is a classical result, and it has faced increasingly serious challenges from the quantum side. In 2016, Hawking, Malcolm Perry, and Andrew Strominger published a paper arguing that black holes may in fact carry what they called soft hair, enormous numbers of low-energy quantum degrees of freedom associated with symmetries of the horizon that had previously been overlooked. If soft hair exists, it would provide a natural repository for the information that falls into a black hole, potentially resolving part of the information paradox. Related work has explored quantum hair in other forms, all with the same general aim of finding hidden structure that classical general relativity misses. None of this overturns the classical no-hair result. Real astrophysical black holes still look, from the outside, essentially like Kerr solutions characterized by mass and spin. But the deeper question of whether the horizon really is featureless at the quantum level, or whether it carries subtle structure that stores the history of everything that ever crossed inward, remains one of the most active areas of theoretical research in physics today. The Great Cosmic Eraser may not be quite as thorough as its classical description makes it appear. So, when we ask what type of black hole an object is, the classification by space-time geometry is answering a different question than the classification by mass. Mass tells us how big it is and where on the ladder it sits. Geometry tells us whether it rotates, whether it carries charge, and therefore what the surrounding space-time actually looks like. Real astrophysical black holes live on the Kerr branch. The other three solutions are the theoretical corners of the map, defining the space of possibilities. Together, they complete the picture of what a black hole, as a purely gravitational object, actually is. We have climbed the mass ladder and mapped the geometry of space-time around a stationary black hole. But there is still an entire dimension of classification we have not touched. Because the same black hole, unchanged in mass or spin or charge, can look completely different depending on what is happening around it right now. A supermassive black hole feasting on gas at the center of an active galaxy outshines every star of that galaxy combined. The very same black hole, if you cut off its fuel supply, would fade dramatically as its accretion flow drained inward. Not the object changes, its environment does. The behavior category is where black hole astronomy connects most directly with what we actually see through telescopes. The most spectacular members of this category are the accreting black holes. An accreting black hole is one that is currently drawing substantial matter from its environment. This is a state, not a mass class. Any black hole of any mass, from stellar to ultramassive, can be in an accreting state or a quiet one. The distinction is behavioral, and the difference in brightness between the two conditions can be more than 10 orders of magnitude for the same object. The reason material falling into a black hole becomes so luminous is subtle and beautiful. If you dropped an object straight into a black hole from far away, it would gain enormous kinetic energy as it fell, but nearly all of that energy would go into crossing the horizon, along with the object. Nothing would come back out. Astrophysical infall is different because of angular momentum. Any parcel of gas approaching a black hole from a real galactic environment carries some sideways motion. That sideways motion prevents a direct plunge. Instead, the material must spiral inward slowly, forming a disk in which each ring of gas orbits at a different speed, with rings closer to the black hole moving faster than rings farther out. Because neighboring rings slide against each other at different speeds, friction develops between them. Magnetized turbulence stirs the disk violently. These processes rob individual gas parcels of orbital energy, allowing them to spiral gradually inward. But the energy that was in orbital motion does not vanish. Much of it is converted into heat. The disk becomes ferociously hot, and hot matter radiates. In a typical accretion disk around a black hole, the innermost regions can reach temperatures of millions of degrees, glowing brilliantly in ultraviolet and X-ray light. By the time material reaches the innermost stable circular orbit and plunges toward the horizon, it may have radiated away between 6 and 42% of its rest mass energy, depending on the black hole's spin. That is far more efficient than nuclear fusion in a star's core, which converts less than 1% of hydrogen mass into radiation. Accretion is the most powerful, sustained energy conversion mechanism in the universe. There is a natural cap on how brightly a spherical, radiating accreting system can shine while still growing. It is called the Eddington limit. If the radiation pressure produced by an accreting object equals the gravitational pull holding the inflowing gas together, further increases in accretion rate blow the gas outward rather than allowing it to fall in. The Eddington limit therefore sets a rough ceiling on the luminosity a steadily accreting black hole can produce in proportion to its mass. It is a balance condition, not a hard law. Real accretion is often non-spherical, and material can plunge in through narrow channels while radiation escapes preferentially through other paths. Under such conditions, systems can appear to exceed the Eddington limit, the so-called super-Eddington accretion state. Some ultraluminous X-ray sources are believed to be stellar mass or neutron star accretors operating in this super-Eddington regime, mimicking the luminosities of much larger objects. The family of accreting black hole systems is huge, and each member has its own name in astronomical literature. But it is essential to recognize that these names refer to configurations, viewing angles, and activity levels, not to different fundamental kinds of black holes. Every one of them contains a black hole with the same kind of event horizon, distinguished only by mass, spin, and environment. At the stellar mass end, we have the X-ray binaries. In these systems, a stellar mass black hole draws material from a nearby companion star, either through direct overflow of the companion's Roche lobe, or through the capture of a stellar wind. The infalling gas forms a small hot disk, and the system emits characteristic X-ray radiation that can be observed across our galaxy. Cygnus X-1 is the classic example. Some X-ray binaries also launch narrow relativistic jets, and when they do, we call them microquasars, because they mimic in miniature the jet-producing behavior of the far more massive active galactic nuclei. GRS 1915 plus 105 is a famous example, ejecting jets of matter at nearly the speed of light for years at a time. Move to the supermassive end, and the same physical phenomenon plays out on a much grander scale. When a supermassive black hole at the center of a galaxy is actively feeding, the entire central region becomes what astronomers call an active galactic nucleus. The accretion disk around the central black hole is enormous, sometimes hundreds of astronomical units across. Its luminosity can exceed that of an entire galaxy of stars. Surrounding the disk is a thick torus of gas and dust, and above and below the disk plane are structures called coronas, hot regions where energetic processes accelerate particles and produce X-rays. Depending on the orientation of the whole system as seen from Earth, and on the strength and duty cycle of accretion, active galactic nuclei receive different observational names. If we happen to view an active galactic nucleus close to face-on, with a direct view down through the corona and disk, we see broad emission lines from fast-moving gas near the black hole, and we call the object a Seyfert-1 galaxy or a broad-line active galactic nucleus. If we see the same object from the side, with the surrounding torus blocking our view of the innermost regions, the broad emission lines are hidden, and only narrower lines are visible. This is a Seyfert-2 galaxy or a narrow-line active galactic nucleus. If we look at the object nearly edge-on to its jet, receiving beamed radiation directly along the line of sight, the object appears as a blazar, one of the most extreme and rapidly variable objects in the sky. Some blazars can double in brightness in hours and vary erratically across the entire electromagnetic spectrum. If the accretion rate is extraordinarily high and the entire system outshines its host galaxy by a large factor, the object is classified as a quasar. Quasars were originally called quasi-stellar objects because they appeared as unresolved points of light in early photographs, indistinguishable from stars, yet showed spectra like nothing else in the sky. It is now understood that quasars are supermassive black holes, accreting near their Eddington limit, embedded in host galaxies whose light is drowned by the central engine. The brightest quasars are so luminous that we can detect them across nearly the entire observable universe. Their existence in the early universe, at redshifts corresponding to less than 1 billion years after the Big Bang, is one of the sharpest challenges to models of supermassive black hole formation. Radio galaxies are another subcategory, defined by the presence of enormous double-lobed radio emission produced by relativistic jets extending far beyond the visible host galaxy. Some radio galaxies show jets stretching hundreds of thousands of light years, ending in lobes of glowing plasma where the jet material slams into the intergalactic medium and decelerates. These structures represent the outward flowing energy tapped from the black hole's spin and its surrounding magnetic field, but never from inside the horizon itself. There is another dramatic category of accretion event that plays out on far shorter timescales. When a star wanders too close to a supermassive black hole, tidal forces stretch it apart, generating a stream of gas that partly falls back onto the black hole. As this material accretes, it produces a bright flare that can rise over weeks and fade over months to years. These tidal disruption events reveal supermassive black holes in galaxies that were otherwise dormant, providing single-shot demonstrations of the presence of a central engine that would be invisible in steady emission. All of these, X-ray binaries, microquasars, active galactic nuclei, Seyferts, radio galaxies, blazars, quasars, tidal disruption events, are accreting configurations, not different fundamental types of black hole. The same underlying object could appear as any of these depending on its mass, its current fuel supply, the geometry of its immediate environment, and our viewing angle. This unified picture, developed over the past several decades, is one of the great achievements of modern astrophysics. Behind the dizzying zoo of names lies a single physical scenario: a black hole, an accretion disk, magnetic fields, sometimes a jet, sometimes an obscuring torus, and radiation escaping through whatever windows the geometry permits. Accreting black holes can also change states over time. A stellar mass black hole binary, in particular, can shift between distinct accretion modes as its fuel supply fluctuates. In a quiescent state, accretion is very low and the system produces only faint radiation. In a soft state, the inner disk extends close to the innermost stable circular orbit. Temperatures peak, and the system radiates predominantly in thermal soft X-rays. In a hard state, the disk is truncated farther out, a hot corona dominates, and the emission peaks in hard X-rays. In some intermediate states, jets can be launched. Transitions between these states play out over weeks to years and have been mapped in dozens of galactic black hole binaries. It is a reminder that the state of accretion is dynamic, not a fixed label attached to the object for life. But not every accreting black hole launches powerful jets. Some do, many do not. Jets appear preferentially in systems with high spin and specific magnetic field configurations, and even those systems do not always produce them. So when we discuss active galactic nuclei or microquasars, It is important not to imagine every accreting system as a jet-producing spectacle. The majority are radiating disks and coronas without any dramatic beamed outflow. Now turn to the opposite condition. A dormant black hole is one that is not currently accreting enough material to produce a bright electromagnetic signal. Dormant is not the same as dead. It is not the same as broken. It is not the same as gone. It is a description of activity level, nothing more. A dormant black hole exerts exactly the same gravity it always has. It is just not currently converting large amounts of infalling matter into radiation, because not much matter is currently falling in. Most black holes in the universe are believed to spend the majority of their existence in a dormant or near-dormant state. Active galactic nuclei and quasars are the brief, bright episodes in the long biography of a supermassive black hole, not its default condition. Our own galactic center exemplifies this quiet state, yet a dormant supermassive black hole is not less of a black hole for being quiet. Its horizon and its gravitational grip on the surrounding stars are entirely unchanged from what they would be if it were feeding voraciously. The same is true at stellar scales. Dormant stellar mass black holes vastly outnumber the accreting X-ray binaries we can easily observe. Finding them is hard. Many hide as invisible companions to visible stars, revealing themselves only through the wobble of the companion's orbit, or through microlensing events as they pass in front of background stars. The Gaia mission has begun to identify several such quiet stellar mass black holes, and each one adds to the confirmation that the majority of these objects are silent, waiting, and undramatic. Identifying a truly isolated dormant black hole is one of the hardest tasks in modern astronomy. An isolated stellar mass black hole drifting through interstellar space has no companion whose orbit can be traced. It captures at best a trickle of interstellar hydrogen atoms, producing radiation far too faint to detect from any reasonable distance. Its gravitational influence on the surrounding gas is minute. The only detection channels are the rare microlensing events, in which a background star briefly brightens as the black hole passes in front of it. Several strong candidates have now been identified this way. Each represents a member of what may be a vast hidden population of hundreds of millions of quiet stellar mass black holes drifting through the Milky Way. We must be careful about claims that any invisible massive companion is definitely a black hole. Dark companions can be neutron stars, white dwarfs, unseen pairs of stars whose combined light is faint, or the products of errors in modeling the orbit. Individual cases have been misidentified in the past, and only after careful cross-checks are the strongest candidates upgraded to confirmed dormant black holes. This is why dormant and isolated black holes remain such an important frontier. Understanding their true numbers is essential for estimating the entire black hole population, not just the bright minority we happen to see radiating. A dormant black hole can become active again if new material arrives. If a gas cloud drifts into the galactic center, or if a companion star begins to overflow its Roche lobe, or if a tidal disruption event delivers a fresh stream of material, a previously quiet black hole can flare into activity. Over cosmic timescales, most supermassive black holes probably alternate between long dormant intervals and shorter active episodes. Our observations of the universe capture only a snapshot of this ongoing cycle. Beyond dormancy, we come to another environmental category: the binary black hole system. Binary here describes the system, not a different kind of horizon geometry. Two black holes gravitationally bound to each other are a binary, regardless of their individual masses or spins. There are several ways such a system can form. Two massive stars in a stellar binary can each evolve, in turn, into a black hole, leaving behind a bound pair of stellar mass black holes. In the dense environment of a globular cluster or nuclear star cluster, individual black holes can find and capture each other through gravitational encounters. Two galaxies can merge, delivering their central supermassive black holes into the merged remnant. And exchange interactions and dense clusters can pair black holes previously bound to other partners. Once a black hole binary exists, it does not remain static. General relativity predicts that any accelerating mass radiates gravitational waves. Ripples in space-time that carry energy away from the system. In a binary, both black holes are constantly accelerating as they orbit their common center of mass. They therefore emit gravitational waves continuously, though at rates that depend on their separation. As energy is carried away, the orbit shrinks, slowly at first, then faster as the black holes approach each other, then dramatically fast in the final moments before merger. The final stages have three characteristic phases. The inspiral phase, during which the two black holes spiral inward through many orbits over minutes, seconds, or even fractions of a second in the final moments before contact. The merger phase, in which the two event horizons make contact and combine into a single, distorted horizon. And the ring-down phase, during which the newly formed single black hole oscillates, radiating away its distortions until it settles into a stationary Kerr geometry. It is worth emphasizing carefully what the merger is not. The two event horizons do not crash into each other like solid balls. They are causal boundaries in space-time, not surfaces of matter. As the black holes approach, the horizons distort dramatically, stretching and warping toward each other. When they meet, they do not collide in any mechanical sense. They merge into a single connected horizon, initially highly non-spherical, which then rings down into a stationary Kerr form. Throughout this process, no matter is ejected from inside either horizon. The mass that is lost to gravitational wave radiation, sometimes several solar masses worth for a stellar merger, is not material carried away by ejected debris. It is the energy content of the gravitational radiation itself, sourced from the shrinking binding energy of the system as it settles into its final state. The gravitational wave signals from these mergers, first directly detected in September of the year 2015 by the LIGO detectors, have opened an entirely new window on black hole populations. The waveform of a merger encodes the masses, spins, and orbital parameters of the two black holes, as well as the final mass and spin of the remnant. Every detected merger becomes a mass and spin measurement. Every observation constrains the properties of the population that produced them. In just under a decade, gravitational wave astronomy has grown from a single event to a catalogue of many dozens, and the flow of new detections continues. Supermassive black hole binaries pose a special problem. When two galaxies merge, their central supermassive black holes are dragged inward by dynamical friction against the surrounding stars. This process is effective at bringing the two black holes to within a few parsecs of each other, a fraction of the distance from the Sun to Proxima Centauri. But at that point, the surrounding stars have mostly been ejected by earlier interactions, and dynamical friction runs out of material to work against. The binary can stall for millions or billions of years at parsec scales without efficient decay mechanisms. This is called the final parsec problem, and it has been one of the outstanding puzzles of galaxy evolution for decades. Proposed solutions involve interactions with additional infalling gas, with a third black hole delivered by another merger, or with the rotating axis-symmetric potential of the host galaxy, providing new orbits that continue to interact with the binary. It now appears that some combination of these mechanisms does allow supermassive binaries to eventually merge, but exactly which mechanisms dominate remains under active investigation. Future space-based gravitational wave detectors will directly observe these mergers when they occur, providing crucial data on how often the final parsec is actually bridged. Finally, we come to a category that captures a black hole's dynamical history in yet another way. The wandering or recoiling black hole is one that has been displaced from where it was originally born. Wandering here does not necessarily mean drifting freely through intergalactic space. It means moving through a galaxy in a way that departs from a fixed central position or a stable orbit. There are several mechanisms that can displace a black hole. In dense environments containing 3 or more black holes bound in a small volume, gravitational interactions can eject 1 or more black holes at high velocity. A binary black hole can be disrupted by a close encounter with a third black hole, sending some or all of them onto unbound trajectories through the galaxy. When 2 galaxies merge, the incoming galaxy's central black hole may not sink completely to the center of the remnant on the timescales of interest. And when 2 black holes merge, gravitational wave radiation can carry momentum unevenly, kicking the newly formed remnant in a specific direction. That final mechanism, gravitational wave recoil, deserves special attention, because it is one of the most striking predictions of general relativity. When 2 black holes with mismatched masses or mismatched spin orientations merge, the gravitational waves they emit are not perfectly symmetric. More radiation is emitted in some directions than others. Because gravitational waves carry momentum, the merger remnant recoils in the opposite direction, like a rocket firing exhaust in one direction and being pushed the other way. The magnitude of this kick depends sensitively on the mass ratio and on the orientation of the 2 spins. In the most extreme configurations, kicks of thousands of kilometers per second have been calculated. Such kicks would exceed the escape velocity from many galaxies, ejecting the merged black hole into intergalactic space entirely. The consequences of these kicks depend on where the merger occurs. For a merger deep in the center of a large galaxy, a modest kick will cause the remnant to oscillate around the center for millions of years before dynamical friction restores it to rest at the middle. A larger kick will send the remnant on a long, wandering orbit through the galactic halo before it eventually settles or leaves entirely. In a small galaxy with a shallow gravitational potential, even a modest kick can send the merged black hole into intergalactic space, permanently unbinding it from the host. A recoiling black hole does not become instantly invisible. It can carry with it part of its original accretion disk, briefly continuing to shine as an offset active nucleus while it moves away from its birthplace. It can carry with it a small cluster of stars that were bound to it before the merger. It can produce tidal disruption events far from any galactic center, revealing its presence when a star wanders too close. And in the future, gravitational wave observatories will be able to identify recoil signatures directly by measuring the mass and spin properties of merger remnants and comparing them to the expected outcomes for different kick scenarios. Some candidates for recoiling black holes have been identified, though nearly all remain contested. An active nucleus offset from the center of its galaxy might be a recoiling remnant, or it might be a black hole delivered by a still ongoing merger, or it might be an artifact of dust obscuration in the true galactic center. Distinguishing these possibilities requires careful multi-wavelength observation. Wandering black holes are also expected within galaxies, not necessarily launched by kicks, but simply left over from earlier mergers with satellite galaxies whose central black holes are still spiraling inward. Simulations of galaxy formation now routinely predict that large galaxies host several such wandering black holes at any given time. None of this implies that large numbers of wandering black holes threaten the solar system. The nearest known black hole is many light years away, and the number of stellar mass black holes drifting through interstellar space is tiny compared to the number of stars in the same volume. The universe is very large and very empty at these scales. Wandering black holes exist, but they do not constitute a danger to any specific location. We have now completed the tour of the 14 major black hole classifications: stellar mass, intermediate mass, supermassive, and ultramassive by mass, primordial and microscopic by origin, Schwarzschild, Kerr, Reasoner-Nordstrom, and Kerr-Newman by space-time geometry, accreting, dormant, binary or merging, and wandering or recoiling by behavior and environment. And along the way, we have met the subpopulations: fallback black holes, direct collapse seeds, merger remnants, tidal disruption event hosts, quasars, blazars, radio galaxies, and more. Before closing, we should be careful about what is not a confirmed type of black hole. Some ideas that appear alongside black holes in discussions of exotic physics are neither confirmed nor properly categorized as black holes. A white hole is a mathematical solution to Einstein's equations describing a region from which matter can only emerge, never enter, the time reverse of a black hole horizon. No white holes have been observed. It is not simply an ordinary black hole running backward. A wormhole is a hypothetical topological connection between two regions of space-time that would, in principle, allow shortcuts between distant points. Some black hole solutions have internal structures that mathematically resemble wormholes, but no traversable wormhole has been observed, and it is not automatically the case that every black hole contains one. A graver star is a hypothetical compact object that mimics the external appearance of a black hole without possessing a true event horizon. A boson star is a similar hypothetical alternative built from a coherent quantum field. A dark star, a fuzzball, and a regular black hole are all speculative constructions from various approaches to quantum gravity, each aiming to resolve the classical singularity in a different way. None have been observationally confirmed, and an analog black hole is a laboratory system, a flowing fluid, a Bose-Einstein condensate, an optical medium that reproduces selected horizon-like behavior for scientific study, without being a gravitational black hole in any astronomical sense. Each of these belongs to a different category. Some are mathematical solutions, some are black hole mimickers proposed as alternatives to horizons, some are candidates within incomplete theories of quantum gravity, some are laboratory analogies used to test individual predictions such as Hawking radiation in controlled settings. but none should be added to the confirmed astrophysical classification alongside the 14 categories we have explored. Now, step back and look at the whole picture. Every classification we have followed answers a different question. Mass tells us where on the enormous scale ladder the object sits. Origin tells us whether it was born from a dying star, from a merger, from a direct collapse, or from the first fraction of a second of the universe. Geometry tells us whether it rotates, whether it carries charge, and therefore what its external space-time looks like. Behavior tells us whether it is currently feeding or quiet. Environment tells us whether it is isolated, paired, central, or displaced. All 5 axes describe the same underlying object. A single black hole can be simultaneously supermassive, Kerr, accreting, part of a binary, and recoiling from a past merger. Every label applies at once because each answers a different question. That is the deepest lesson of the 14 category framework. Black holes are not 14 different species competing for the same niche. They are the same physical phenomenon, a region of space-time bounded by a one-way causal horizon. Presented at wildly different scales, formed through wildly different histories, and observed in wildly different environments. The horizon is the constant. Everything else is context. From the smallest stellar remnant of a few solar masses, drifting silently through interstellar space, to the 60 billion solar mass central engine of a distant quasar blazing across the observable universe. Every black hole is a variation on the same fundamental theme. The universe contains a spectrum of these objects that spans 10 orders of magnitude in mass, several formation channels, 4 possible geometries, at least 2 dramatically different activity states, and multiple dynamical positions relative to the galaxies that host them. When we ask what type of black hole an object is, we are choosing which of those axes to answer along. And when we understand all 5 axes together, the 14 categories stop looking like a confusing menagerie and start looking like what they really are. A coherent map of one of the most extraordinary phenomena in the entire cosmos.